Okay, let's get started. So let us start the discussion on Ssd modulation. For the moment, let us consider the synchronized system. So the model of interest is given below. So you take m of t multiply by a product modulator, then here you put a 2 cos omega ct. See, in the previous case I used a root 2 and here I am using 2. So it won't make much difference, but it will simplify our algebraic manipulations. Okay. So after modulation you put a SSB filter, otherwise both the bands will be transmitted, upper sideband and lower sideband. So either you remove the lower sideband or upper sideband. For that purpose you put a SSB filter, and then you transmit to the channel. In the channel noise is getting added, n of t, and then you put a band pass filter centered at a frequency of C, and then in the demodulator you are going to use synchronous demodulator. So here I am going to use cos omega ct, and after that put the low pass filter to remove the high frequency component, and then you get a output. Okay. So this is the simple block diagram of your SSB system, both transmitter and receiver. Okay, if you notice here, I put a different constant in different models. Sometimes I put a root 2 cos omega ct, and sometimes I put a 2 cos omega ct. Okay, so basically the idea is I put a constant such that the input power to the receiver is SI. In every case it is expected. So in every case it is m square is equal to power is E of m square of t. Just want to keep the same signal power which is coming into the receiver input. So to keep it uniform, it is a matter of scaling, nothing else. So it doesn't affect the result in any way. Even if you put 5 times cos omega ct, then also it will be fine. 5 cos omega ct or cos omega ct, it doesn't affect my analysis, but it will make you very complex of deriving this formula. That is why the derivation will be complex. Even if you don't put this 2, doesn't matter, you still get the same result, don't worry. So only for convenience we are putting this 2 times cos omega ct. Okay, that's it. So what is the purpose of the SSB filter? The SSB filter which removes one of the sideband. See, after a double sideband suppressed carrier modulation, your signal will contain like this. Let's say this is your m of f, recall from your amplitude modulation, then your modulated signal x of f will contain like that. So this is fc and this is minus fc. And what is this guy? These are lower sidebands. And what about this one? Upper sideband. So either you transmit upper sideband or lower sideband. So for that you have to remove the any one sideband. That is the reason we put this SSB filter. So the SSB filter removes any one of the sideband. Then you will transmit over the channel, and the channel is again is going to be assumed to be ideal and ideal band pass filter. The only effect there is the presence of noise n of t, which adds to the channel. So at the receiver you will have a band pass filter with a center frequency of fc, and then we have the demodulator. This is my demodulator. Okay, so in this point I need to find out what is SI, what is NI, and here at the output of the demodulator I need to find out S0 and N0. Okay, so this whole thing is my channel. let's say channel. So that's our system which we need to analyze. Okay, so let me call this point is A and this point is B. Okay, actually this whole thing is the receiver, I mean including this part and this part, whole thing is receiver, and this part is demodulator. Demodulator is a part of your receiver, because in the receiver you have a, I'm sorry, it includes from this point only. Okay, this whole thing, this is my receiver. Okay, and this part is going to be the demodulator. Therefore the demodulator is a part of the receiver, because in the receiver you have front end amplifier, receiving antenna, then IF amplifier, then local oscillators, mixers, right, RF amplifiers, IF amplifiers. There are many stages, so those things will not come into the part of demodulator. So demodulator is this part. So before the demodulator, what is the input signal power and what is the input noise power? After the demodulator, what is the output signal power and output noise power? Okay, so that's it. Now let us take 2 points here. This is point A and this one is point B. So it is more meaningful or useful to talk about the noise power at the output of the band pass filter at point B, that is the front end of the receiver, sorry, front end of the demodulator, because at point A if you try to calculate the noise power, what is the noise power? See, at point A, the n of t is coming as it is, right? So what is n of t? N of t is n by 2 for all the frequencies, n by 2 for all the frequencies. This is s suffix n of f. Okay, at point A, the noise power, what is the noise power? The height is n by 2. What is the width of this range? Infinity. Therefore the noise power becomes infinity at the input of the band pass filter. So it will not make any sense to talk the noise power before the band pass filter. It is much more meaningful to talk about the input signal power and input noise power immediately after the band pass filter. So that's what we are doing now. So what is the at point A, what is the transmitted signal? So at this point your signal is m of t times cos of omega ct 2 times m of t cos omega ct. And after the band pass filter, what is the signal? That signal is going to be m of t cos omega ct plus Hilbert transform of m of t times sin omega ct. Okay, and this plus sign indicates we are retaining the lower sideband. Okay, that means we are transmitting the lower sideband, and rejecting the upper sideband. And so what is point A? At point A, how do you write the mathematical expression? At point A, this signal is added with the n of t. So let me say this is my y of t, y of t is equal to m of t cos of omega ct plus Hilbert transform of m of t m cap of t sin omega ct plus n of t. This is my signal before the band pass filter at point A. Is that okay? Fine. Now let us try to find out the power of the message signal. How do you calculate? Now if you take like this, if you take both the upper sideband and the lower sideband, what is the power? In the time domain, it is m of t. Here also in the time domain, I put Fourier transform. In the time domain, this is 2 times m of t cos omega ct. What is the power of 2 times m of t cos omega ct? It is 2 times m square of t whole bar. But you are not transmitting the upper sideband and lower sideband, both the bands. See, this is the power of both the lower sideband and upper sideband. But what we are doing is we are transmitting only one sideband. Therefore, either lower sideband power or upper sideband. This is upper sideband and this one is lower sideband. So, what is the lower sideband power? It is m square of t. What is upper sideband power? It is m square of t, bar of t. Half of that. Okay. Therefore, if you look at this figure, then in this point, what is the power? Power is 2 times m square of bar of t, and in this point the power is m square of t bar. The same power also coming here, m square of t bar. The same power is because ideal band pass filter, and here also the power is m square of t bar. So, output of the band pass filter, the power is m square bar t. Okay. So, that is it. Therefore, in this point my signal power at point A, signal power is equal to how much? M square bar. What about the noise power at point A? It is infinity, of course. Noise power at point A in the above figure, it is infinity because it is a white Gaussian noise. At point A, the noise is white Gaussian noise. See, n of t is white Gaussian noise, and this is my point A, and you are giving to band pass filter. And in this point, my power spectrum density will be n by 2, that is from minus infinity to plus infinity. So, in this case, if we calculate power, then how much power does it have? Infinity. Okay. So, basically the idea is to normalize the input signal power in every case to m square of t. That is the reason we multiplied by this 2. So, SI is the power at the input to the demodulator. So, this is the input power to the demodulator. So, m of t root 2 times cos of omega ct. Now, in this, what is the signal? M of t 2 times m of t cos omega ct. If you take Fourier transform, you will get m of f minus fc plus m of f plus fc, right, by 2. So, the 2 will get cancelled. Therefore, power in this point is how much? m square of t bar. Now you are putting a single sideband filter. So single sideband filter means it removes one sideband and passes the other sideband, and this power is power of both USB upper sideband plus lower sideband. Upper sideband has the power of 2 will come here, 2 times m square of t, it is m square of bar of t, and lower sideband has the power of m square of t. If you add these two, then you will get 2 times m square of t bar. Therefore output of the SSB will be same m square bar of t power, and in this noise is getting added, okay, white Gaussian noise. So this point also again the power will not be changed, m square of t, and then you are passing it to ideal band pass filter at the frequency. Therefore this point also the power is m square bar of t, power will not change. So and again you are giving to the product modulator, and this point is the input noise power and the input signal power. Therefore input signal power is equal to m square of t bar. So okay, so let me call this as point B. In the point B, let me denote the signal is yi of t. What is yi of t? This point we already wrote, okay. So what is the signal for this point? We can easily write down. So this point I know the signal mathematical model, so that I already wrote here. Y of t is at point A, the signal is y of t is equal to m of t cos omega ct plus m cap of t sin omega ct plus the noise n of t. This whole thing is passed through a band pass filter. So after passing through the band pass filter, your yi of t, this point it is yi of t, and this point it is, what is the notation that I used for this? Y of t, y of t. So y of t is equal to m of t cos omega ct plus m cap of t sin omega ct plus n of t. And what is y suffix I of t? This is at point B, and this is at point A. At point B, yi of t is equal to, after band pass filtering. So this guy is a band pass signal, so it comes as it is m of t cos omega ct plus m cap of t, Hilbert transform of m of t times sin omega ct plus this n of t is white Gaussian noise, white Gaussian noise. After passing through a band pass filter, it will become narrowband noise, okay, narrowband Gaussian noise. The narrowband Gaussian noise is represented by using in phase component and quadrature phase component. N suffix c of t cos omega ct plus n suffix s of t sin omega ct. So therefore this guy represents signal part, and this one represents noise part to the input of my demodulator. Okay, and this one is the quadrature representation of noise that is coming out of from the band pass filter at the receiver. This is what we are going to give it to the receiver. Now let us combine the in phase and quadrature phase components. So m of t plus n suffix t of t multiplied by cos omega ct plus m cap of t and then ns of t multiplied by sin omega ct. This is my input to the demodulator. So this yi of t is given to the demodulator. My demodulator consists of a multiplier. So here I will put let me put 2 times cos omega ct and then followed by low pass filter. Now let me say this point is y1 of t. What is y1 of t? y1 of t is equal to y suffix I of t multiplied by 2 times cos omega ct. Now what is yi of t? This is m of t plus n of t multiplied by cos omega ct plus m cap of t plus ns of t multiplied by sin omega ct. Whole thing is multiplied by 2 times cos omega ct. Okay, so this is going to be 2 times m of t plus n of t cos square omega ct plus m cap of t ns of t multiplied by cos omega ct times sin omega ct. Now how do you simplify this expression? Okay, what will be the output of the your product multiplier now? So how do you simplify this? See, here I have cos square omega ct. I can write down in terms of 1 plus cos 2 omega ct. Okay, but what about these two terms? These two terms, sin omega ct and cos omega ct, both are orthogonal signals. Orthogonal means their product will be 0. So therefore the second term will disappear. Okay, so I can write this as 2 times m of t plus n of t times cos square omega ct becomes 1 plus cos of 2 omega ct by 2. So this 2 and that 2 will cancel. That is the reason we are multiplying them by 2. Okay, otherwise that the denominator will get 1 by 2. You multiply inside m of t plus n of t plus m of t plus n of t multiplied by cos 2 omega ct. Okay, this is passed through the low pass filter, and the low pass filter is like this, but this guy is somewhere at fc. So therefore the second component, this will be removed by the low pass filter. Low pass filter will reject. So output of my low pass filter y naught of t is equal to m of t plus, sorry, this is nc of t, n suffix c of t, not n of t. I forgot to put that suffix, in phase component, and here also n suffix c. Okay, so n suffix c of t, in phase component. So the low pass filter removes the cos 2 omega ct term. Therefore output of the detector is m of t plus nc of t, and this m of t is the signal part, output signal, and this one is output noise of the demodulator. And it is once again, what is the power of this? S naught is equal to m square of t bar. What is the noise power? Noise power n naught is equal to nc square, like this. Now n naught is how much? What is the bandwidth of the band pass filter? Again, it is not 2b, okay, it is simply b. Okay, please remember that your signal has either lower sideband or upper sideband, like this, lower sideband, and here also lower sideband. What is the bandwidth now? Here B, and here also it is B. Therefore B times n by 2, and here also B times n by 2. Therefore this is NB, total noise power. N0 is equal to NB. It is simply because this band pass filter has a bandwidth of only B hertz. If you look at the figure, where is it figure? Yeah, this band pass filter has the bandwidth of B hertz only. It doesn't have the bandwidth of 2B hertz. Okay, so that's it. So again, this is the same as your SI. S0 is equal to SI. Then your N0 is equal to NB. Now what is your output SNR? S0 by N0 is m square of bar of t divided by NB. This is the same as SI by NB. What is SI by NB? If you recall, this is the same as your baseband communication system. Again, your SSB system also performs the same as your baseband communication system and DSBSC system. Therefore, as far as the noise performance is concerned, DSBSC and single sideband modulation systems are not different from each other. So essentially, when you go from, let's say, baseband to AM with a double sideband suppressed carrier and a single sideband, the considerations are different. It is not because of better performance of noise. Okay, why did we go for SSB? To save the bandwidth, right? We did not go to the SSB because it gives some other advantage. So we went to SSB only. The reason is it gives better bandwidth efficiency. It is not because you like to have a superior noise performance. It is simply to save the bandwidth. Okay, so in no way your SSB is superior compared to DSBSC in terms of noise performance. The SSB has the advantage over DSBSC by having lesser bandwidth. You can save the bandwidth. Instead of 2B, you can use simply B. So if it is DSB, what is the bandwidth requirement? Bandwidth requirement is 2B. And if it is SSB, what is the bandwidth requirement? It is B hertz. That means what? You are saving the bandwidth, but you are not getting the performance in terms of noise compared to DSB-SC. So it is expected. So incidentally, as far as the bandwidth is concerned, in some sense, in some sense, okay, DSB and SSB are the same because there is no performance improvement against noise. Because in DSB, although the bandwidth is twice, you know that by using quadrature amplitude modulation, you can transmit 2 messages instead of 1, right? Using DSB-SC, you can go for quadrature amplitude modulation and you can transmit 2 messages. 2 messages over bandwidth of 2B. Therefore, what is the bandwidth of single message? Again, B hertz. And here also the bandwidth is B hertz. So if you use quadrature amplitude modulation, then there is no saving of bandwidth between DSB-SC and SSB. Therefore, for all practical purposes, they are equivalent if you can exploit that in a particular application. So therefore, once again, S0 by N0 is equal to m square bar divided by NB. This is my gamma. So the figure of merit as far for all the system is concerned remain the same. It is equal to gamma. Okay, now let us talk about the noise performance in VSB vestigial sideband with the suppressed carrier system. Similarly, when you go from single sideband modulation to vestigial sideband modulation with a suppressed carrier modulation and carry out a synchronous modulation, follow the same process using the same argument that we have used in this lecture. Okay, so you will get the more or less same answer. Remember, you have a very similar quadrature representation for the VSB SC signal. For SSB SC signal, what is your modulated signal? Your modulated signal x of t x SSB is equal to x SSB of t x SSB of t is equal to m of t times cos of omega ct plus Hilbert transform of m of t sin omega ct. Similar kind of expression you will get a vestigial sideband modulation also. Okay, except that this m cap of t is no longer the Hilbert transform. Okay, so this m cap of t is a signal obtained by passing m of t through a appropriate filter, what you call the VSB filter. In vestigial sideband modulation, what you do, instead of this you will be having something different. However, the details are a little complicated, but not too much. So this more or less same exercise, same procedure what we have done for your SSB, but instead of this m cap of t, you will have its equivalent of its corresponding representation. And in VSB SC, you can show that your signal to noise ratio, output signal to noise ratio is the same as n naught is the same as gamma by n, Si by Nb, this is once again gamma. So whether it is DSB SC, whether it is single sideband modulation, whether it is VSB SC, vestigial sideband suppressed carrier modulation, the performance of the system after synchronous demodulation is the same. Okay, so the performance of the system after synchronous demodulation is the same as that of the baseband system. Same as baseband communication system. There is no improvement as far as noise is concerned. So really you are not achieving anything in terms of SNR performance. So when you are when you are doing amplitude modulation, you are not achieving anything in terms of signal to noise ratio performance. So that is the message, and that is the moral of the story. Okay, that's what we need to understand. Okay, so let me stop at this point. The next lecture I will consider an example problem. Okay, let me work out one example problem. Okay, thank you very much.